This video is about electrical transformers. Transformers are all around us, but pretty much go unnoticed and definitely underappreciated. Without transformers, civilization as we know it would not be possible. This is a rather small power distribution transformer. There is a link below to videos which show much larger transformers being transported by road and rail using very special trailers and rail cars. The transformer shown here is a step-down transformer. It's used to reduce voltage from transmission lines, which may be at several 100,000 volts, down to tens of thousands of volts, which is then fed to transformers like these, where the voltage is reduced again to the nominal voltages that enter businesses and homes. In this video, we'll be dealing with small transformers like these and the materials from which they're made. Before we get into the theory of how transformers work, I want to show you some various mechanical configurations of transformers. And here we have an assortment of foot-mounted transformers. That is, they have mounting feet on them, and printed circuit mount transformers. And these two transformers right here are of the same volt amp rating. The only difference is the way in which they're mounted. Now here you can see this transformer is rated at 100 volt amps. The primary is 115 volts and the secondary is 10 volts. Now they're not rated in power, they're rated in volt amps. That's because I could power an inductor with this that would draw 10 amps, but that would be drawing no power. Because of the current being at 90 degrees with respect to the voltage. So the transformer can supply 10 volts at 10 amps at any angle between the voltage and the current. Now here's a transformer that has various taps, both primary and secondary, so it's possible to get all kinds of voltage and current ratings by series and parallel operation or connections. Now this is a microwave oven transformer. It's been removed from a microwave oven, and it's kind of a special thing, although by theory it works the same as any of these other transformers. It has a special weirdness about it that we'll get into. Here are two examples of variable transformers. The input to these is your normal line voltage, or mains, and then here's the output, which is variable by turning the knob here. This one's capable of 10 amps continuous, and this one's capable of 20 amps continuous. This one also has a built-in voltmeter. Now this one is a brand name of PowerStat. Another popular brand name is Variac, and you'll hear Variac used a lot, but that's actually a brand name. And these are variable transformers, sort of like Kleenex and facial tissue. Now these transformers are also what's known as an auto transformer. Now not all auto transformers are variable, however, and we'll get into what makes an auto transformer as compared to an isolation transformer. There's also some tricks you can do with these that are not normally talked about. They can act as a variable inductor for a project, and also they can be used as a variable load on another transformer that you might be testing. And that's kind of a strange thing, but I'll show you how that is done. Here's some examples of current transformers. This one is made to plug into a multimeter, and it can be clamped onto a current carrying conductor, and it has a ratio of 1,000 to 1. So there's 1,000 turns on the secondary, and typically there'd be a single turn on the primary. The wire would go through here. So reading 1 milliamp on the meter would mean 1 amp going through here. Now, of course, you can also pass a wire through here several times if you want to be able to measure lower currents. The same is true for these transformers. These happen to be printed circuit mount transformers, and this one's rated 200 amps and it's 1,000 to 1 turn. So again, you can measure the milliamps on the secondary or connect a resistor to read a voltage. So these are available from Digikey. And you can also make your own current transformer. This is a typical power transformer that I've removed one winding, and you can pass whatever you want that'll fit through the window here. You could pass a single, like a number 8 wire, or maybe even a number 6 wire would fit through there if you want to measure large currents. And it's a very handy device to have in your home laboratory. Now here are some ferrite cores suitable for making high frequency transformers. These are called toroidal cores, I can hardly say it. And there's your typical shape. Most transformers are made with E's and I's, and you can get these as sets like that with a bobbin for winding your own high-frequency transformers. And we'll use this to make a transformer ourselves and show how it works and some of the fundamental problems with making transformers. Now, if you look closely at these transformers, you can see that the core is made up of laminations, and this is to reduce eddy current losses, which would occur if it would be a solid piece of steel. So these type of transformers are usually made up of E and I laminations. So that being an E and this being an I, there would be a layer with that orientation. Then the next layer would go this way with an I placed up here. And it would be built up that way around the bobbin. In order to understand transformers, we need a little bit of theory. Now, I've made some videos earlier on inductors and capacitors. They're linked below, and I suggest you look at those to understand inductors really well. A transformer is really an inductor with two windings on it. So if you understand inductors very well, you'll understand transformers also. So here's a very simple equation. It's called the law of induction. It can be derived from Faraday's equations as well as Lenz's law. But the equation is that the voltage across a coil of wire of n turns is equal to the number of turns times the rate of change of flux through those turns. So in words, it's E equals minus N d phi dt. And if we're only going to deal with sine waves as we talk about transformers. And so if we have flux going through a core that is a sine wave in intensity, the rate of change of that flux is also a sine wave that's shifted 90 degrees. Here the rate of change is 0, and on the 0 crossings, the rate of change of flux is maximum. So this is time in that direction. So if we apply a voltage to the coil, we'll get this d phi dt and this flux. And if we have this flux going through the coil, we'll get the voltage. So everything is bidirectional because of that equal sign. But the flux is determined by the current. And we don't have any current in our equation here yet. So we need a little more information. When we apply a voltage to an inductor, we will get a current. And this current is given by I equals the voltage over the inductive reactance. And if you watched the videos on inductance, you know that X sub L is equal to J omega L. So the inductive reactance, the J indicates a 90-degree phase shift basically, and omega is equal, omega equals 2 pi times the frequency f. So when you plug XL in there, you get the current. So it's the current that's determining the flux. Okay, now if we put another winding on our inductor, let's put a core through it first. So that represents a coil of wire around a core of magnetic material. So if we put a second winding on there, let's call this E1, we'll get E2 out here. And the ratio of those voltages is approximately the ratio of the turns in the coils. That's not quite true, but we'll talk about that later. So at this point, let's look at the core in a little more detail. Okay, when we apply an AC voltage to an inductor that has a laminated core, there are three kinds of losses in the core. We already mentioned eddy currents, and that's the reason that the cores in line-powered transformers are laminated. to minimize eddy current losses. There's another phenomenon known as hysteresis, and magnetic materials are not necessarily linear, and due to the nonlinearity, some losses occur. And the third type of loss is called magnetostriction, and that's a case where the actual volume of the core changes with the amount of flux going through it. Now, for small transformers like we're talking about, this isn't very important, but in large power transformers, power distribution transformers, that can be a major factor. In fact, this magnetostriction actually causes the ground to shake near these large transformers because of the huge mass of the core, and the fact that the core is large physically means a lot of magnetostriction will occur. So at any rate, these things determine what we do with the core. For a equivalent circuit of a transformer, these losses are usually represented as a resistor in parallel with the winding. Now this would be a fairly high resistor because these losses are fairly small compared to the IR losses, the IR drop losses in the transformer. So we know that windings have resistance. This is usually shown as a resistor in series with the winding, and the secondary will also have some resistance. Now, the primary coil generates flux. Now, not all the flux ends up going through the secondary. So we have what we call leakage flux, and therefore we end up with a leakage inductance. This represents the inductance of this winding only that is not coupled to the primary, and vice versa. So this is typically the equivalent circuit of a transformer. We have primary coil losses due to the resistance of the winding, the same in the secondary. We get slight voltage reductions due to leakage inductance, and we have core losses. Now, when we apply a voltage to the primary, there's a current that flows through the inductance of the primary, and this is called the magnetizing current. And even without a load on the secondary, we will get current in the primary. Again, it's determined by the inductance of the primary winding. So it turns out these losses here are maximum when there's no load on the transformer. And that's because the voltage across this coil is maximum. As we start to load the secondary, the primary current will go up, and we'll get more of an IR drop across that resistor. So it doesn't change very much, but just applying the voltage to the primary makes the core start to work. Well, there's another type of transformer we need to touch on briefly, and that's called the auto transformer. Now, an auto transformer is a transformer with only one winding. So can tap off of a single winding, and we don't have isolation, but we do have voltage step up or step down. I could apply a primary voltage here and get a higher voltage out there. And that's what an auto transformer is normally used for, either step up or step down, where isolation between primary and secondary is not required. Now, of course, there's usually a core also. Now, the term auto does not mean automatic or anything like that. It means self, like in autoimmune disease. That's the connotation, not automatic. Now, we briefly touched on variacs and power stats, which are variable auto transformers. And the way they're made is we have a wiper that can touch every winding up and down. So as you turn the knob, the wiper goes up and down along the winding. And in that case, the input is typically here, and then this is the output, usually to a receptacle. Now, some of them actually can go a little higher than the line voltage. So the wiper can go right on up to that point. So you can get low voltages or even higher voltage than the AC line. And I'll open one of these up for you so you can see how it's made. So I think that pretty much covers our theory stuff. And it's time to go have some fun now. Okay, here we have a transformer. It's being powered from this variable transformer, so I could set the correct primary voltage. And in series, here's the wire from the variable transformer, and then we're going to go through a current meter and back to the primary of the transformer. Now this is a 100 VA volt amp transformer. So I have it on AC amps and on the 300 milliamp position. So I'm going to turn on the voltage, and we see we get about 120 milliamps of current flowing in the primary with nothing connected to the secondary. And it turns out the core of the transformer works the hardest during no load conditions. When we attach a load, we get some high R drop on the primary from its resistance, and therefore a slightly lower voltage applied to the inductance. Now this is called the magnetizing current of a transformer, and the inductance of the primary with no load on the secondary is called the magnetizing inductance. So if we put a load on this transformer, the primary voltage, internal voltage after the drop due to the resistance of the winding, will produce a slightly less flux than under the no load condition. Okay, I ran some tests on some other transformers as well of various volt amp ratings, and here would be the normal full load primary current, and here are the currents under the no load conditions. Here's the transformer that we just looked at, and we can see we get a current of 14% of its full load rating with no load connected. And on a slightly bigger transformer, the number's a little lower, and in a bigger transformer it goes down some more. So as the transformer size goes up, they tend to use more iron and copper, and to try and keep not only more efficiency in the transformer, but also it ends up with a lower no load or magnetizing current. Now, as I mentioned, the microwave oven transformers are really strange. We normally have a full load rating of 8.3 amps, and we measure 6.1 amps, and that's 73% of its full load rating when operating at no load. And let's take a look at why that is. Okay, here's the microwave oven transformer, and it's kind of hard to see, but in here there's a little stack of laminations on each side, and these form a magnetic shunt. So the flux from the primary, some of it will go around in this path. Not all of it will go up through the secondary coil. And the same is true on this side. Some of the primary flux will go through these laminations rather than up through the secondary. And this gives the transformer a nonlinear action, which apparently is desirable for the magnetron in the microwave oven. Now, this little stack of laminations can be removed. You can just drive them out with a hammer and a wooden dowel. But you'll find then that the primary current under no load goes up even higher. So you would need to add turns to that primary to keep from saturating the core. If you intend to build this into some other device, like if you want to make a little welder or whatever, you'll have to take care of that situation. Let's measure the primary resistance of this transformer. I have a meter here set on ohms, and we're reading around 4.5 ohms. Now, previously I measured my test leads and they were 0.1 ohms. But a thing to be aware of, if a transformer is operated under full load conditions for a long period of time, it'll get pretty warm. And this resistance will actually go up by as much as 40%. So we may be approaching 6 ohms on a fully hot transformer. Here's a variable transformer that we looked at earlier, and I've removed some screws so we can take the knob off and remove the case, which is hard to do with one hand. And inside we see a toroid core that's wound with a single layer of magnet wire where the insulation has been removed off the top and it's been ground flat somewhat. And in there is a carbon brush to make contact with the coil. So when you turn the knob, this picks off a voltage between 0 and something even higher than the applied line voltage. So that's basically how a variable auto transformer works. Okay, here I'm going to show you an unusual way to use a variable transformer to match a load of a low voltage. Here we have our 100 VA transformer. It has a 10 volt secondary. Since it's 100 VA, that must be rated at 10 amps. I'd like to load this transformer to 10 amps, perhaps to see how hot it gets or whatever. And to do that, I would need a 1 ohm 100 watt resistor. Since I don't have that, I'm going to use this variable transformer to match the load to a 150 watt lamp. And what we're going to do is connect the lamp to the input to the variable transformer, and the output of our transformer under test we will plug in to the output of the variable transformer, and then we should be able to adjust the turns ratio until we get a 100 watt load into this lamp. Now let me show you schematically what this looks like. Okay, here's our transformer under test. We're going to plug it into power, and then the 10 volt secondary we're going to plug into the output of our variable transformer. And then with the clip leads, we're going to connect what would normally be the input of the variable transformer to the 150 watt lamp. Now, one thing we want to be sure not to do is turn this to 0, or you will be shorting out this transformer. So I'm going to start somewhere near the middle and slowly bring the wiper down to the 10 volt position, and then we should be getting a higher voltage out of the transformer and into the lamp. Okay, our transformer is plugged in, and the output is connected to what is normally the output of the variable transformer, and our lamp is connected up. And as I turn the transformer down, the lamp is coming on. There, I turned it back down. So let's put the amp meter and I'm going to adjust the transformer for our 10 amps. Okay, there we have approximately a 10 amp load, and the light bulb it's not at full brilliance because it's a 150 watt light bulb, and we only have about 100 watts going in there now. So this is one unorthodox way to use a variable transformer, actually using it backwards. Okay, here's our same setup, but this time I've replaced the light bulb with a transformer from a microwave oven. Now, we showed earlier how the magnetizing current of this transformer was around 6 amps. So we can use that as an inductive load, just like we used the light bulb as a resistive load. So as I bring the turns ratio down, we see the current going up. And there's approximately 10 amps. It's difficult to get exactly because of the voltage step between just one turn in the variable transformer. But basically, there's a 10 amp load with essentially no power dissipation. We're drawing inductive current, which is 90 degrees out of phase with the voltage. Therefore, there's current draw, but there's no dissipation other than normal core losses, which are typically pretty low. So this demonstrates why transformers are rated in VA rather than watts, because you can draw inductive or capacitive current just like you can draw resistive current. This is a neon lamp. It takes 90 volts to ignite it. So it's a good indicator of voltage. And here I've wired a neon lamp to the primary winding of our good old 100 VA transformer. The turns ratio of the transformer is roughly 12 to 1. So if I energize the secondary with 1.5 volts, I should get less than 20 volts on the primary. And I have it wired with a little switch here. And when I push the switch, nothing happens. But when I release the switch, the lamp fires, which would indicate we have at least 90 volts at that time when the switch is released. So there's nothing when I push the switch, but it fires when I release the switch. And in a moment, we'll get into why that's happening, but I want to show something else here. Okay, I've attached a 1 amp diode onto the secondary winding. That's the 10 volt winding. And with an alligator clip, I'll attempt to connect it. Now when I push the switch, the lamp never fires. Now I'll remove that diode and do it some more. So without the diode, we get the flashing, but when we connect the diode, it no longer flashes the lamp. And let's go to the whiteboard and see what's going on. Okay, here's our setup with the neon bulb and the transformer and the 1.5 volt battery. Now when we close the switch, the voltage is never high enough to light the neon lamp. But when we open the switch, we see the neon lamp flashing. Now the voltage, again, here's our law of induction, E equals ND phi dt. So when we have a high voltage, we must have a large rate of change of flux with respect to time. And we also know that flux is proportional to the current. So let's look at a plot of our current here. When we first close the switch, the current's going to increase at the L over R time constant of the transformer. But when we open the switch, the current can go to zero very quickly. So here we get a very fast, high rate of change of current. So we get a large rate of change of flux, or dφ/dt. So we get a rather high voltage induced, at least 90 volts, enough to light that neon lamp. Now when we put the diode in the circuit, now the neon lamp no longer flashed when we opened the switch. And what's happening there is the current going through this winding now has a place to go when we open the switch, and it goes through the diode and decays at the L/R time constant of the winding. So now, instead of the current going to zero quickly, it'll decay naturally at the L/R time constant. And you'll see diodes like this in a lot of inductor circuits, relays and solenoids and things like this. And that's its purpose is to prevent the generation of high voltages. And when a diode's used that way, it's called the reverse diode, or a reverse rectifier, or a flyback diode. And it's a very common way of eliminating high voltage transients. Earlier I said we'd make a transformer and see what we can learn from that. And here it is. I've taken a ferrite toroid, and I have a winding of 10 turns and a winding of 20 turns. So this would either be a 2-to-1 step down or 2-to-1 step up transformer. Let's measure the inductance of these windings and see what we can learn from that. Okay, I've hooked up the 10-turn winding to this inductance meter, and it's showing approximately 100 microhenries. Now let's see what the other winding is. Okay, here's the 20-turn winding hooked up to the meter, and it's showing 390 microhenries. And from a theoretical standpoint, if that were 400 microhenries, that would tell us that the inductance goes with the square of the turns. And that is a fact with any inductive configuration where most of the flux goes through a core such as this. So we can say that the inductance is proportional to the number of turns squared. Well, what can we learn from our quickly homemade transformer? Well, first of all, we learned that the inductance of a winding goes up with the square of the number of turns. So what would happen if we applied 120 volts at 60 hertz to the primary of this transformer? Well, the inductive reactance is J omega L. Let's ignore the J. That just tells us there's a 90-degree phase shift. So at 60 hertz, omega is 377. Now the current, this would be the magnetizing current. The magnetizing current is the current that flows in the primary with no load on the secondary. And it's the magnetizing current that establishes the flux in the core. So if you crank through these numbers, you end up with 795 amps. Now I doubt that the wire on this transformer is going to handle that amount of current. It might handle 1 or 2 amps. And of course the core might saturate at a very high current as well. So since the inductance goes up with the square of the turns, let's go 10 times the turns. That should give us 100 times the inductance, which should give us 100 times less current. And that's still quite a bit of current, almost 8 amperes. So let's go 10 times more turns. Now the inductance goes up by another 100 times, and the current comes down to something fairly reasonable, roughly 80 milliamps. So I doubt that we could get 2,000 primary turns and 1,000 secondary turns through this core. But what if we went to 100 kilohertz and applied 20 volts to this transformer? So if you go through the numbers, just plug these numbers in on the previous equations there, and you end up again with roughly 80 milliamps. So this transformer might perform very nicely at 100 kilohertz, but at 60 hertz it's not going to work as a transformer. We would need a much bigger core and a lot more turns to work at the lower frequencies. Well, I hope you got something out of this video. If you did, please give us a thumbs up and consider subscribing. So I hope to see you in our next video.